Very good. Hello and welcome to today's Flan Talk. We are excited to have Satwik with us today. Satwik is a PhD student at the University of Oxford and supported by Google DeepMind. And his primary research interest lies in the realm of learning, language learning algorithms with a keen focus on expressiveness and learning capabilities of neural networks. And Satwik was actually one of our first Flan presenters when he talked about the ability and limitations of transformers to recognize formal languages. And today he will present to us his recent paper on the simplicity bias in transformers and their ability to learn sparse Boolean functions. So thank you for joining us today, and over to you, Satwik.
Yeah. Hello, everyone. I am Satwik, and I'm a third-year PhD student at Oxford. And I'm very excited to be here and talk about our work on simplicity bias in transformers. So this work was done over a year ago with some colleagues here at Oxford and at Mila, Montreal. So let's get started. So as you all know, transformers are kind of like the go-to architecture for language modeling, and large-scale transformers work quite well in practice. On the other hand, since transformers do not have a hidden memory vector that they can update iteratively, they have some limitations in expressing certain kind of formal languages like parity, particularly in finite precision setting. Whereas recurrent neural networks, they can pretty much express all regular languages in finite precision setting. And moreover, in some of our prior experiments, we have observed that transformers struggle on various formal languages compared to LSTMs, the recurrent models, and even other recent works have had similar observations. So broadly, what we were interested in is to just understand why transformers generalize well or work so well in practice, and why do they perform better than LSTMs despite their weaknesses in modeling formal languages. So this is, of course, this is a very fundamental question, and we don't have a direct answer, a concrete answer to that. But to understand why transformers generalize so well, we explored this notion of simplicity bias in transformers. And based on some observations we made there, we were trying to identify or find some formal languages or some precisely defined functions on which transformers can perform better than LSTM. So today, in the first part of the discussion, I'll talk about simplicity bias in transformers and in general. And in the second half, I'll talk a bit about some experiments on Boolean functions in particular. Okay. So this idea of simplicity bias comes from trying to understand a very fundamental question about deep learning. And that is like, why do deep learning models generalize so well or work so well in practice? And this is obviously a very basic thing, and I'm sure most of you are aware of it, but I'll just quickly introduce this. So like, as you all know, deep learning models are very expressive and they can express large class of functions. And because of that, they have very high capacity measures like VC dimension or arithmetic complexity and so on. And what that implies is that the worst case sample complexity bounds for these kind of models is quite high. But if we train neural networks in practice, then they generalize well with much fewer examples. They don't overfit, and that kind of goes against some of the intuition. So in other words, the kind of problem that people have been trying to understand is if you have a sample set S with M examples, let's say like 1,000 examples, then there exists, if you take a large feed-forward network, then there exists one network that can get zero training error and may have 10% test error. And there can have another, there can be another feed-forward network that can get 0% training error, but can have 20% test error, and another that has 30% to 40% test error. So, but if we train a model with SGD and we initialize it and train with SGD, we typically find that they generalize well. They don't have like 40% test error if they have 0% training error. So, I mean, just with an example, with simple visual example, suppose you have two sets of examples, and these are linearly separable, and this is the target function that is used to label these examples. Now, if you take a large neural network, then it can possibly represent this kind of decision boundary and fit all the examples perfectly and achieve zero training error. And there would exist another neural network that can represent this kind of decision boundary, and this will also achieve 0% training error. And maybe another one that can represent this. But if we randomly initialize a model and we train it with SGD, we'll find that whatever it learns, it will be closer to this than these other weird looking function. And it won't be exactly like this, but it is likely to learn something that generalizes well and is simple. So the question is, why does this happen? And this is a very fundamental question, and we don't know the exact reason behind this yet. But the general consensus in the community is that there is some form of implicit regularization in neural networks, and that is often referred to as simplicity bias, and that may refer to multiple things. But the idea is there's some kind of implicit regularization in the learning algorithm. And in the last 10 years, there have been a lot of works along this, and there have been some works that have provided strong evidence to suggest that SGD has some beneficial properties, which kind of biases the learning algorithm to converge, or the neural network to converge to functions which are of low complexity in some sense. But more recently, there has been evidence to suggest a different hypothesis. And what they argue is that while SGD has a key role and it does obviously have some beneficial properties, it may not be the primary source behind the regularization in neural networks. And the argument goes more like this, that the parameter space and loss landscape has a larger role. And the idea is, if in the parameter space of neural networks, most of the functions are of low complexity, then any local search based optimizer is more likely to find a low complexity function. So, and I'll talk more about this in a bit. But maybe I'll also like to mention that about a year or so ago, there was a talk given by Professor Ard Louis on this topic in this Discord server, and I think the video is on YouTube. So if you're interested there, then please check that out. Okay, so first we'll look at some experiments around simplicity bias and transformers, and before that, I'll just quickly introduce a few definitions. So in our work, we primarily work with Boolean functions, which are over bit strings of fixed length n, and the output is always 0 or 1. So it will always be a binary classification problem. And we'll focus on a particular complexity measure called sensitivity, which kind of indicates how likely it is that a function value will change due to some small change in input. And so more formally, the sensitivity of a function at a particular input x, so it indicates how many indices are there such that if you flip the bits in those indices, then the output of the function will change. And the sensitivity, in particular average sensitivity, over all functions is just the average of this over all inputs. And in the context of our work, well, when we say sensitivity of a function, we'll particularly refer to this average sensitivity, which is also normalized by length so that we can compare it across various lengths in a more uniform manner. So what this sensitivity of a function, what this kind of indicates is that if you just sample a Boolean input uniformly at random, and then you pick an index uniformly at random, and you flip it, then how likely is it that the output of the function will change? So if we look at some examples, let's say we refer to this parity n function, and for a string of length n, so this parity n function, so this will output 1 if the number of ones in the input is odd, and it will label 0 otherwise. So here all the bits are important, all the bits are relevant. You count the number of ones. If it's odd, then the label is 1. So this function, you can see that this has a sensitivity of 1, because no matter which input you pick and which index you pick, if you flip the bit, then the label will change. So this function has the maximum sensitivity. And then there's other variants, like if you look at sparse parity, where the parity is computed over exactly k bits. Suppose we have 100 bits and only some 3 bits are relevant, and the parity is computed over those 3 bits, then the sensitivity of that will be k by n, or 3 by 100. Okay. So why do we focus, or why do we care about sensitivity? So intuitively, you could think that like functions which have low sensitivity are in some sense simpler functions, and simpler functions are more likely to generalize. So intuitively, there's more like an Occam's razor like kind of argument. But more formally, we know that functions which have low sensitivity also have low complexity based on various other measures. For example, low sensitivity functions also have low Kolmogorov complexity, although the other way around is not true. But low sensitivity functions also have low complexity in various other measures, such as like the degree of the Fourier representation of a Boolean function, or the depth of the decision tree required to represent a Boolean function, and so on. But then there's a question that does low sensitivity imply low generalization error? And that's not necessarily true. So there have been works in the past that explore correlation between low sensitivity and sensitivity and generalization in the context of Boolean functions, and also in more general terms with some other extensions of sensitivity. And they find some correlation, and we also do that a bit in our paper. And well, you can see some correlation in like practical tasks, or if you do some experiments, but if you do not know that the target function has low sensitivity, then it's I don't think it's possible to kind of give any form of guarantee about generalization. Okay, and another reason behind adopting sensitivity is that we can estimate the sensitivity of a function by sampling examples. So there are various other complexity measures over Boolean functions. So for example, there's some others we explore, like the size of the Boolean expression required to represent a function. And there's in some past works I've explored this Lempel-Ziv complexity. But for all these measures, if you have a function over 0, 1, n, or n-dimensional Boolean inputs, you need to know the value or the label of the function on all 2 to the power n inputs. So as the input length grows larger to, let's say, get 20 or 30 or even more, then it becomes more and more computationally intensive and almost impossible to compute the complexity of those functions. But with sensitivity, we can kind of sample like tens of thousands of examples and get an estimate of what the sensitivity of the function is. Okay, so I've mentioned this term like parameter space a couple of times, and I'll just describe what that is. It's very simple. So suppose we have a model that has 2 parameters. We have something like a feed-forward network or transform with only 2 parameters. I don't even think that's possible, but let's assume that is like it can have 2 parameters. And let's say we have a machine such that it can only have values. The parameters can have values between -1 and 1. So there are 2 parameters which can have values between -1 and 1. So now the parameter space of this model is any point in this square, and each point in this square represents some function. So suppose we pick a particular theta1, which is 0.5, and another value for the other parameter theta2 is 0.8. And if we restrict the domain to be just Boolean inputs, and suppose we restrict the domain to be Boolean inputs of length 3, then this model will have some labels over all the inputs in this space of like Boolean inputs with 3 dimensions. So there's 2 to the power n inputs. So for each point here, it represents some Boolean function. All the points need not represent unique or different Boolean function. There could be repetitions and everything. But each point here represents some Boolean function, and what we are interested in is what are the complexity of those Boolean functions. Suppose this is the parameter space of transformers or LSTM, let's say, then are most of these functions, do they have low sensitivity, high sensitivity, or are they uniformly distributed? So how does it look like? And the way that we try to find that out, it's very simple. We just apply a very basic Monte Carlo method. And suppose if we have transformers, then what we do is we sample tens of thousands of transformers. And for each of the sampled model, we estimate the sensitivity of the model. And then we try to look at the distribution of that. And here, so these are the distribution of sensitivity for various sampled transformers and LSTMs. And suppose so these are all with input lengths 20, and the models have 2 layers and a width 256, and all the parameter values are sampled between -10 and 10. So now if you look at this plot, what we find is that so most of the transformers that we sample have very low sensitivity, much lower sensitivity compared to LSTMs. And what this kind of shows is that if you just look at the parameter space of transformers, then most of the points here will be functions of low sensitivity. And this is true even if we sample from some other distributions, like if we sample from normal distribution with various standard deviations or uniform distribution with other range. But if we sample from sample very small values close to zero. So for example, if you sample from Xavier normal or Xavier uniform distribution as well, where the values are very close to zero, then actually even their LSTMs, most of the LSTMs also have very low sensitivity. Although like it's larger than transformers, but it is still a lot smaller than the distribution here. Okay, so I'll just give a very quick example of a particular kind of function. So suppose our inputs are of over dimension 5. So their inputs are of 5 bits, and we are looking at a particular type of function like parity 5. So this parity 5, it outputs 1 if the number of ones in the input is odd, and it's output 0 otherwise. And there's another function in this parity 5 that outputs 1 if the number of ones in the input is even. So there are two functions. Both of in one case, if the number of ones are odd, then the label is 1. In the other case, the label is 1 if the number of ones is even. Okay. So now if we have inputs of length exactly 5 or like 5 bits inputs, then in total there are 2 to the power 5 possible inputs. And over that, there's 2 to the power 2 to the power 5 possible Boolean functions. So there's over 4 billion Boolean functions. And out of those 4 billion functions, only 2 of them are this parity 5 functions. And if we sample uniformly over all these 4 billion Boolean functions, then the probability of obtaining one of these parity 5 function is less than 1 in a billion. Okay. But what's interesting is that if you uniformly sample 2-layer LSTMs 10 million times, then we find that 1 in 30,000 of them represent a parity 5 function. So which is like 60,000 times more likely than like sampling from uniformly overall Boolean function. But on the other hand, if we sample transformers 10 million times, so none of them represent a function which computes this parity 5 or which is equivalent to this parity 5. In another word, what that means is that if like you have this parameter space of LSTMs, then the volume of the functions or the volume of the parameters that represent this parity 5 function is a lot more in LSTMs than in transformers. So after this, I'll talk a bit about the relevance or some potential implications of this, but I'll take a pause here if anyone has any questions about whatever I've talked about so far. Then maybe we can ask them.
Seems like there are no questions. Thank you for stopping for us, though.
Yeah, okay, all good. So, of course, you might wonder, so why do we care about randomly initialized model? So why do we particularly care about this? So let's look at a very simple learning algorithm. And so this will do a very stupid thing. So this is not a practical learning algorithm, but what we'll do is, so suppose you are given a set of training examples, like 100 examples. What we'll do is we'll sample we'll sample a transformer, let's say, with some parameter values between -1 and 1. And then if we find that the transformer is consistent with all the training examples, we'll return that and use it to make our predictions on the test set or unseen examples. But if it is not consistent with the training set, we'll sample a model again. So we'll keep sampling the models until we find one that is consistent with the training set. So now we have some distribution over the values of the parameters. That leads to a distribution over the set of all Boolean function. And that is the prior of the, so when we are looking at this distribution by sampling model, so we are actually looking at the prior over all the Boolean functions. And now if we apply this kind of algorithm, then the probability of picking a function among all the functions that are consistent with the training set. So that is the posterior of the function. Suppose we have, in total, we have 1000 functions, but 50 of them are consistent with our training set. Now, which of them is more likely to be picked? So that is all determined by the posterior distribution. So now with a simple Bayes rule and everything, so it's actually very straightforward to see that if you had this kind of sampling algorithm, then which of, and if you just apply, you follow this procedure, you apply the sampling algorithm, then which function that you end up with, so that is kind of primarily determined by the prior over the function. So the posterior distribution here is primarily determined by the prior here. So suppose if you have a model such that the prior is heavily biased towards functions of low sensitivity. And there are functions of low sensitivity that are consistent with the training set as well. Then when you apply this kind of sampling algorithm, you are more likely to pick that or those kind of functions over others. But now the question is, but why does that matter? Because in practice, we don't sample models, right? We initialize the models and we train them with SGD. So what is the relation between sampling models and training with SGD? And this particular question was actually extensively explored in a particular paper. So I'll talk about a couple of papers now, just quickly. So this paper is SGD a Bayesian sampler? Well, almost. So in this paper, what they do is they try to compare the functions or the posterior that you get by this kind of Bayesian sampling algorithm with those of functions that you get by training with SGD. And to do that, they do a pretty simple thing. So you reformulate the data set, like MNIST data set, as a binary classification problem. And what you do is you train a feed-forward network 1 million times. So you initialize 1 million different feed-forward networks. You train each of them with SGD on the data set, and each of them, let's say, gets 100% training accuracy. And then you have a test set with 100 examples, and you make predictions with these 1 million models on those 100 examples. So now if you have 100 examples, even over those 100 examples, the total number of possible labelings it's 2 to the power 100, which is a lot more than a million, right? So, but what they find is that, so suppose if you train a model with SGD 1 million times, so there are particular kind of labeling, like if you look at this point, so this is a particular labeling over 100 examples. And this particular labeling happens 10% of the time. So out of 1 million uh, training instances with SGD, 100,000 of them lead to this particular labeling over 100 examples. And if you look at this point, this is one particular labeling that happens 1% of the time. And this one happens, let's say, 0.1% of the time. But what is quite interesting is that if you train with this kind of Bayesian sampling approach, then those functions appear almost the same number of time with this other approach. So if you do this 1 million times with the Bayesian sampling approach, then that same function also appears 10% of the times, and this same function appears 1% of the time. So these two distributions are, in that sense, what they found is that they are heavily correlated. And yeah, so that's like a very simple description of their work, but they do this across multiple architectures like ConNets, feed-forward networks, LSTMs, and on different kinds of data sets. And one thing also, yeah, so this is a pretty interesting paper and worth checking out. And I'll mention another paper quickly. And I think this was one of the most interesting papers in ICLR 23. And what they do is they actually apply this exact same algorithm that I mentioned earlier, sampling between -1 and 1. So in this paper, they had a bit more fancy algorithm, but in this, lost landscapes are all you need. So in this paper, what they do is they train a model with just sampling, which they call guess and check. So you guess the parameters. If it's consistent with the training data, you use that to make prediction. And they do this for MNIST and CIFAR 10. And what they find is that even if you just apply this kind of guess and check algorithm, then the test accuracy that you get is very competitive with models trained with SGD. And so if you can look at numbers here, then for all these numbers, we'll find that even with guess and check, the test accuracy that you get is very close to the models trained with SGD. Now, of course, this guess and check algorithm is extremely inefficient, and that's why it's difficult to train models on a set of examples beyond like 32 or something. But they also apply a bit more like sophisticated algorithm, which are quite simple as well. But these are also not gradient based, and these are also like the sampling based algorithms. So what they do is this pattern search and random greedy. Suppose your model has 100 parameters. So what you do is you first pick them uniformly at random. Then you look at the first 10 parameters and you add some noise in that and you check whether your training accuracy increased. If it increased, you keep that and you move on to the next set of like 10 parameters in the next block and you add noise again. And if it doesn't increase the training accuracy, you add noise again. So you keep adding different kind of noise and you see if, but you do it iteratively across different blocks of parameters. And so this is like a simplified description of the algorithm. But with this, they're able to fit a larger set of examples, like say 1000 examples. And here you can see that even without an SGD based algorithm, these models still get about the same test accuracy as SGD on like MNIST and CIFAR 10. And what the evidence from these work suggests is that the gradient dynamics are not necessarily the primary source of regularization in training neural networks, and it has more to do with the landscape of the parameter space or the loss of like neural networks. Okay, so now I'll talk about some experiments with Boolean functions, but if anyone has any questions about these, I'll just wait for a few seconds. Okay. Okay, so what we observed was that okay, if you randomly sample models, then it seems like there's a bias in transformers towards low sensitivity functions. But we were interested to see what happens if we train them with SGD, the gradient-based algorithms, and is there any differences between the kind of functions that they learn, like transformers and LSTMs. And what we first do is a very simple thing. We create multiple data sets with Boolean inputs. And so each Boolean input is sampled uniformly at random. And we label them 0 or 1 uniformly at random. So these are just labeled by random Boolean functions. And suppose we train both transformers and LSTMs on the same training data. And there's no evaluation here. They're just labeled by some function. Now we know that if we train them with SGD, they'll fit the data set and get 0 training error. But they won't necessarily learn the same function when they fit the data set, right? So what we look at is what is the complexity or the sensitivity of the functions learned by these models at different iterations of training and at convergence. So here, these curves show, so for example, the blue curve here, it shows the sensitivity of transformers at different iterations of training when trained on this dataset with 1000 examples. And the red one shows the same thing for LSTMs. And what we find is that both models seem to learn functions of increasing sensitivity or increasing complexity in some sense. And transformers typically converge to functions of lower sensitivity than LSTMs. And these results also echo some prior observations about feed-forward networks. So there's this very popular paper you might have come across, SGD neural network learns functions of increasing complexity. So there are some other measures, but in principle, their idea of the observations are similar in the sense that the model have simple functions initially and they learn more complex functions during training. Although like those measures are not, you can't apply them in a straightforward way to discrete inputs, but there's still some relations to prior work. So for example, there's this paper on the spectral bias of neural networks where they argue that feed-forward networks with ReLU activation, so they are biased towards functions of low frequency. And I mean, you could say that functions of low average sensitivity also usually are functions of low frequency as well. So in some sense, these observations are reminiscent of some of these prior works. And so these are now these are the sensitivity of LSTM and transformers on convergence. So all these points here, so these functions all achieve 0 training error. So essentially you get a transformer, you train it, and that fits the data set perfectly. But the function that it represents actually seems to have lower sensitivity than the function that LSTM finds to fit the data set. So we also did some experiments with some natural language data sets. So we have kind of extended Boolean sensitivity in a very straightforward way, like actually in a couple of different ways. But we extended it for like natural language data. The details are not very important, but what we found is that if we applied that for transformers LSTM trained for sentiment classification tasks like SST and IMDb, So in both those cases, we also observe the similar thing where both the models kind of learn functions of increasing sensitivity during training. And particularly for the sentiment classification task, we find that both models converge to function of like similar sensitivity. I mean, so here it's not very surprising because both the models actually get almost the same test accuracy. So they probably like learn maybe like similar functions, but it's interesting to maybe see that they learn iteratively or increasingly high complexity during training. Okay. So motivated by some of these observations that we described earlier, so we were trying to think, okay, so think of like some well-known Boolean functions that have low sensitivity, like particularly like sparse Boolean functions. And we evaluated the performance of transformers and LSTMs on these like k-sparse Boolean functions. So these are very simple. So a function is Boolean function is k-sparse if its output depends on at most k bits. So suppose you have this input of 14 dimension and there's just 3 bits which are relevant. So the output of this function depends on just these 3 bits. So if you just change the other bit, that doesn't influence the output of the function. So what we do is, so in the following experiment, so we'll have training sets of fixed size, and we'll train the models on them, and we'll kind of tune the hyperparameters, find the best model, and look at their performance. And we'll look at say k-sparse functions where so we in the training data, the inputs are sampled uniformly over Boolean inputs, and they are labeled by some k-sparse function. And in the particular case where this k-sparse function computes the parity over these, like say 3 bits, then it's called like sparse parity function. Okay. So now when we do this, so in this plot, so these show the training and validation curves of transformers and LSTMs when trained on k-sparse functions. So in this case, the inputs are of length 50, and so only 5 bits are relevant. And the plot on the top left, it shows the training accuracy of transformers at different iterations of training. And but transformers actually even generalize well when there's even noise in the training data. So in this particular case, like 10% of the inputs have their labels flipped. So there's 10% noise in the training data. The validation, the test set is completely clean. But what we see is that transformers, uh, they kind of ignore all the noisy examples and they get 90% training accuracy. But on validation, they get 100% test accuracy. Whereas for LSTMs, they get 100% training accuracy and they fit the data completely. But on test data, they don't behave like better than the null accuracy or the majority label for a particular function. And even in this case, if we look at the sensitivity of the models at different iterations, then what we see is that here also transformers and LSTMs both learn functions of increasing sensitivity in some sense. And transformers, they converge to functions of about the same sensitivity as that of the target function. So whatever function we use to label the examples. But LSTMs, when they get 100% training accuracy, they fit the training data. So they actually learn function of higher sensitivity than that of the target function. So when they are fitting all the training examples, they are learning something that is of higher sensitivity than that of the target function. Okay, and then we look at this particular case where the inputs are not just any k-sparse function, but they are sparse parities in some sense. And in that case, we observe this weird behavior where so transformers they don't seem to learn anything for a while, and then suddenly there's a sharp increase in performance, and they get 100% training and validation accuracy. Whereas even for LSTMs in this case, they they get 100% accuracy on the training set, so they fit the training set and completely, but on test set they don't perform better than chance level accuracy. And these are where the inputs are of length 40 and there are 4 bits which are relevant and the parity is computed over 4 bits. And actually even when um, this the training accuracy is kind of the same for transformers. So even there we observe that if you look at the sensitivity, even there we observe like a behavior similar to this, where even though the training accuracy is constant, but the sensitivity of the underlying function of the transformers, it seems to increase, and then they like converges to 0.1, which is the sensitivity of target function here. So I'll just quickly make some remarks about the sparse parity problem. So this is the learning parities is like one of the most well-studied problems in learning theory, in cryptography, and so on. And even though like it's known to be efficiently learnable in the standard like vanilla pack model, but in actually a restricted model of learning, it's known that you need at least like n to the power k steps to correctly learn the parity function. And the main idea is that whatever that restricted model of learning called statistical query learning framework, so that kind of captures gradient-based learning methods as well. So that gives a lower bound on the number of steps you need to learn with a gradient-based method, at least in the finite precision setting. And so these results that we look at here, so transformers actually only learn parity or sparse parity for small n and k, so small lengths and where small number of bits are relevant. So if I increase this to 100, let's say, and there's like 105 bits are relevant. So if this was parity 105, then transformers don't work well at all. And if you increase that to like 500 and where 50 bits are relevant, then even a model of the same scale as GPT-4 will probably fail to learn the correct function. And another thing to note here is that actually this result with LSTM, so this is also for a certain length, beyond a certain length. If you just look at inputs over very small lengths like 20 or 15, then even LSTMs succeed in generalizing well. And one thing to note here is that this, because so here when we look at LSTMs overfitting on the data set, so that is primarily because we have a training set of fixed size. So if you sample a fresh batch of examples during each step of training, then of course like no model can overfit on the data set because it's always new, or each batch of examples is new. But what we find there is that for parity of this particular like 40 length 40 where 4 bits are relevant, even if we train LSTMs for millions of steps, they still fail to find the correct function. um, and with and they overfit if the set of examples is fixed like 50,000. And transformers, they succeed like this particular curves are for training sets with 50,000 examples. But even when there's smaller number of examples like 20,000, 10,000, 5,000 as well, they succeed. But if you as you make the size of the training set smaller, then of course transformers will also overfit. Like at 1,000, if you only have 1 or 2,000 examples, then particularly for the case of parity 44, so transformers also overfit. So here like that this doesn't imply that transformers can never overfit or LSTMs always overfit. It depends on the size of the training set as well. Also, I would like to mention that when we were working on this, there was another paper that explored this problem of like learning parities or sparse parities with neural networks. And it was this paper, Hidden Progress in Deep Learning. And they actually theoretically explore how feed-forward networks, particularly like 2-layer or 3-layer feed-forward networks, how they learn sparse parities and how or why we observe this kind of training curve where it seems like nothing happens for a while and then there's a sharp increase in performance. And in their paper, they also have some similar experiments, particularly with transformers as well, apart from feed-forward networks. And I think over a year ago, or about a year ago, one of the authors of this paper, Iran Malak, I think he gave a talk on this as well in this Discord seminar. So I think the talk must be on YouTube. So if you're interested, you can check that out as well. Okay, so I'll pause again if anyone has any questions about the experiments or anything.
Hi, Satwik.
Yeah.
In one of your previous papers on the
But I'm not able
ability
to
of
hear you.
transformers
Sorry. Is it only me
Can
or?
you hear me now?
Yeah, I think now I can hear you.
Okay, sorry. In your previous paper on the ability and limitations of transformers to recognize formal languages, you experiment with both transformers and LSTM's ability to recognize parity and find that LSTMs are able to generalize very well in comparison to the transformers. But here we find very poor performance.
Yeah, so these are so these are very fundamentally different problems. So like I told you, wait, I'll give this example in the beginning. So in that paper, actually, the parity we were looking at was actually a very different problem. It's the parity with two-state automata, where the inputs are of variable length and all the bits are important. So you can get an input of bits which is of length 10 or 100 or 150, and then you need to count the number of ones there, and then you predict if the number of ones are odd, your label is 1 and 0 otherwise. But here, our inputs are of fixed length, and the parity is only computed over a subset of bits. So for example, so if you look at this figure, so if your input is of this form, then suppose these three indices are relevant. So then you check if is the number of ones in this odd. So here there are 2 ones for these 3 bits. So the label will be 0 for this. And if the number of ones were odd, then the label will be 1. So here only k bits are relevant and not all the bits are relevant. And that actually makes the problem a lot more different and much harder actually. So it's a different problem in that sense. These are not directly comparable.
Okay. Sorry, I missed that detail that we are now only looking at k-sparse parity.
Yeah, so and just I'll mention one more experiment now, which is also related to this full parity. So I'll talk about. But yeah, is there any other questions? Yeah, maybe one other thing that could be useful to mention is that, so here these experiments with LSTMs, these are both with and without learnable positional encodings, which are, so because here you could see that the kind of task depends a lot on finding the right indices and what function there is over that. So of course, like position matters here. So these are not just results with LSTMs without positional encoding. So yeah, so maybe that's worth mentioning.
Cool, thanks.
Yeah. Okay, so I'll just end with one more experiment. So in this case, actually, we have do this, we call it like a mixed parity data set. So you have a data set where half the examples are labeled by a sparse parity function, which depends on, let's say, just k bits. So here the inputs are of length 30. So the sparse parity function actually depends on 5 bits. And the rest of the examples over the full like parity n function where all bits are relevant. So half of the examples are labeled by the sparse parity function, half of the examples are labeled by the full parity, the parity n function. So now if we train transformers on this data set, what we find is that their training accuracy converges at around 75%. And what we find is that they only fit the examples that are labeled by the sparse parity function, and they ignore all the examples that are labeled by the full parity function, where all bits are relevant. And on the other hand, if you train LSTMs, then they get 100, but they fit the data set entirely. And their evaluation for the test performance is very different as well, where transformers, they achieve 100% accuracy on the examples that are labeled by sparse parity, but get 50% accuracy on the examples labeled by the full parity, where all bits are relevant. And similarly, on the other hand, for LSTMs, they actually get 100% accuracy on examples labeled by the full parity function, but only get like chance level accuracy on examples labeled by the sparse parity function. So this kind of like indicates a bias, difference in bias of the two models, where transformers, when they see the set of examples, it's easier for them to optimize their loss and by finding like the sparse parity function, whereas with LSTMs, they seem to be like picking up the full parity function more easily. And maybe like one thing that is worth mentioning is that like some of the prior observations I mentioned along simplicity bias in the parameter space and so on. So those things are not an explanation for these kind of observations with the experiments on sparse parity or like k-sparse function. So we actually, based on those observations, so that was the motivation behind picking these class of functions and doing these experiments, but they may or may not have anything to do with the performance of transformers and LSTMs. Yeah, that could be due to other reasons as well. Okay, so just in summary, what we found is that like functions of low sensitivity, in some sense, overrepresented in the parameter space of transformers, And while both transformers and LSTMs, they learn functions of increasing sensitivity, transformers seems to typically converge to functions of low sensitivity compared to LSTMs, at least on Boolean functions. And then on several case pass functions, you find that transformers generalize well, whereas LSTMs overfit on the training set. So we talked about a couple of functions here, and we also explore some other kind of case pass functions in our paper. Okay, so thank you. And anyone has any questions?